little introduction. So hi everyone, and welcome to the 2026 Statistically Speaking webinar series, which is brought to you by the Data Science and Analytics for Precision Rehabilitation, or DAPR Center, and the Repro Rehab Training Program, both of which are funded by the Eunice Kennedy Shriver National Institute of Child Health and Human Development. This year, the focus of our webinar series is to equip rehabilitation researchers with principled, phase-appropriate approaches to sample size planning, ranging from feasibility and pilot studies to clinical trials and effectiveness research. So my name is Keith Lohse. I'm from Washington University in St. Louis, and ordinarily I'm the moderator for these webinars. But today I will actually be the one doing the presenting. As you can see on the slide here, the title of my talk is Reporting a Power Analysis or Other Sample Size Justification in a Paper. So let me go ahead and actually toggle to my other slide deck. And just as a reminder, for this first part of the session, we'll be recording. So if you have, kind of clarifying questions or things you want to ask, maybe pop those into the chat, and Octavio and I will try to monitor the chat. Octavio will probably be monitoring the chat better than I can. So if he sees like a good opportunity to like jump in and ask the question, he can ask your question from the chat. After a certain point, we'll transition into a more kind of open-ended Q&A where, basically people can like, unmute themselves, ask whatever kind of questions they need. That part won't be recorded. But the recording we will post on YouTube later, so you can always follow up with some of this information. And share with any of your colleagues. The other thing that I'll put in the chat right now is a link to a GitHub repository, and I'll share this again a little later in the talk. But this has a PDF of all the slides that I'm going to go through. It also has some of the code that I'm going to show when we actually get to doing some of these power analyses. Specifically in R. So there's like R code and then like an HTML file where you can kind of follow along. Before we get to the coding part, though, I just want to talk about some conceptual things with respect to power analysis and what we mean when we talk about, sample size justification across different contexts. So as I mentioned, my name is Keith Lohse. I'm an associate professor at Washington University School of Medicine. I don't have any, commercial conflicts of interest, but my salary is supported as a co-investigator on several grants from the NIH and the DoD. I also get to serve as a member of the ASA's Scientific and Public Affairs Committee, and I teach data science skills to biomedical researchers through NIH-funded initiatives like Repro Rehab and the DAPR Center, which many of you are probably familiar with, but if you're not, I would encourage you to check those things out. Like I mentioned, the slides and the code for this talk are available on that GitHub repository that I shared the link for. And if you have any follow-up questions, you're always free to email me. But one of the other services that DAPR offers is what we call DAPI Hour, which is a bad joke on happy hour, where people can drop in for questions related to things about data science, analytics, or precision rehabilitation. So if you scan this QR code, that will take you to the DAPR webpage, where you can then actually like sign up for one of our DAPI Hour consultation office hours over Zoom. All right. So to give people a little bit of background about sample sizes and why we care so much, science in general suffers from a positivity bias in the published literature. So this is pretty well documented since about the 1970s, that oftentimes we tend to favor statistically significant and surprising effects over null results. One of my favorite illustrations of this, though, is from this Van Zvet and Kator paper in 2021, where they did a large-scale automated review, pulling millions of z-values, or I think actually technically they were pulling millions of p-values from papers and abstracts published in Medline. They then converted those into z-values so that all of the statistical results could be shown on the same scale. And this is the distribution of results that they found. So if you're familiar with kind of how the normal curve works, right, we would expect that there would be this nice continuous distribution with a big mass kind of around the mean. And with z-values in particular, if it's less than 0.198, would be a statistically significant result in one direction. And if it's greater than positive 0.198, that would be a statistically significant result in the other direction. And you'll notice then that in between those two limits, there is a conspicuous absence of non-significant results in the published literature. And again, there's like lots of reasons for this, things related to their sampling methodology or how they're counting it, but we can't probably explain it all away without bringing bias into the conversation, right? There clearly we've kind of favor publishing statistically significant results over no results. Another problem that we're facing right now is what's problems of replication, or what is sometimes referred to as the replication crisis. This has been documented from fields from, clinical psychology to, cancer biology. So it affects everyone to differing degrees. Here, I'm going to show data from a recent replication effort in sport and exercise science because that's a pretty closely aligned field with rehabilitation science where we all work. And if you look at this figure here, here are the original studies. And in orange, they show the effect size and 95% confidence interval from the original study. And then in blue, it's the replication team's attempt to go in and replicate what was done in that original study. So these span a lot of different types of interventions and a lot of different types of outcomes, but this is in essence a really high quality, best faith effort to replicate what was found in the original study. And only 28% of the analyzed studies demonstrated what these authors called robust replicability, and that had to meet three conditions. The result had to be statistically significant if the original one won as well. It had to be in the same direction of effect, and it had to be a similar magnitude of effect, meaning that basically the observed effect size had to be within the sampling range of the original effect size. So by that definition, only 28% of studies actually replicated, which means 72% of studies did not replicate, which is bad news from a scientific perspective because we would like to be able to trust, the direction and the magnitude of the findings that we see in a published paper. So, how does this tie into sample size planning? Well, underpowered studies contribute to this bias and contribute to a lack of reproducibility. And we can see this with some simulated data that I've shown here to make what's known as a funnel plot, where I've made up a hypothetical effect. Let's say I have some intervention that changes my outcome by 5 points. And that's what the dotted red line here represents, the hypothetical true value of a mean difference of 5 points. And then I've simulated, a bunch of pretend randomized controlled trials that either have sample sizes of 100, sample sizes of 60, or actually, sorry, that's an N per group. So a total sample size of 200, total sample size of 120, total sample size of 60, or a total sample size of 20 down here. And you can see that as my samples get smaller due to sampling variability, my results get more variable, right? As we increase the size of our samples, we get less and less disagreement between repeated experiments. The other wrinkle to this is if within these simulations, I then color code the results into what was not statistically significant from what was statistically significant, you can see an interesting bias in the distribution of significant effects as our statistical power gets worse. When we have really large samples, we get a pretty unbiased estimate of the real effect. But when we have really small samples, the only results that are statistically significant are the ones where we basically got lucky and we happen to observe a really large effect. So statistically significant results from underpowered studies tend to be really bad estimates of the true effect size. This is sometimes referred to as the winner's curse, which is based on the idea that if you go to like an auction and you outbid other people for an item, you're the winner, but you also probably paid more than that was objectively worth, right? So the idea that because statistical significance rewards extreme values, we tend to grossly overestimate the real effect size if we have an underpowered study. And similarly, then, if now you think about not just any one study, but kind of the history of research in an area, we might get one study that finds a statistically significant effect out here, but then someone comes along and does the next study, and they might get a non-significant result. But it's actually probably a better estimate of what the underlying true effect is. And this is sometimes referred to as the Proteus phenomenon, where what we'll find is across different areas of research, initial preliminary results in a field start out really big and really exciting. And then as more people continue to study it, the effect size gets smaller and smaller. sometimes settling on a more modest but real, effect size, and sometimes ultimately going to zero. And we learned that the original result was a false positive, and we shouldn't have really trusted it to begin with. So this is where, it really becomes important to start thinking about how many observations do we need in our study so we can have more confidence in the results of any one experiment. And a good way to understand that is taking a step back to kind of traditional basic statistical testing. So this is where we're going to contrast the null hypothesis with an alternative hypothesis to better understand statistical power. So most of us, right, we're familiar with the null hypothesis. When we do a statistical analysis, we're used to assuming the null hypothesis as our starting point. And that, like in most cases, to use the randomized controlled trial example, is that there's no difference between my two groups. So the true mean difference is zero if the null is true. And here I'm just simulating several thousand randomized controlled trials to show you how they stack up over time, like a little sandcastle. If I was theoretically able to keep repeating this experiment infinitely, what would happen? And what would happen is it would cluster around zero, but occasionally I'm going to get an extreme negative or an extreme positive result. And if I set my type 1 error rate to 5%, then I'll only have 5% false positives, right? Those are the red dots over in the tails of our distributions. The null hypothesis is true, but if my alpha is set to 0.05, 5% of the time, right, 2.5% in this tail and 2.5% in this tail, I'll get a statistically significant result, even though the null hypothesis is true. Then we can contrast that with what happens if a specific alternative hypothesis is true. So let's say instead of zero being the real effect, what if there really is an effect? What if my intervention changes my outcome measure by 6 points? Well, now we can see that the sandcastle starts to stack up, right, in a similar way with a similar spread, but it's centered on 6. And now if I color code these points, you can see, about half of them actually end up being statistically significant, and about half of them end up being not statistically significant. And if we actually did this, an infinite number of times, we would get these very nice normal curves, or technically, I guess these would be t-distributed, these t-distributions that maybe you're used to seeing in statistics textbooks, right? So we've got our one curve, which assumes the null is true. It's centered on zero, and it has our statistical significance cutoffs at, basically about 2 standard deviations away from the mean. Anything that we observe that falls outside of those cutoffs is statistically significant, and we're going to be excited, that we have a statistically significant result. But in this case, if the alternative hypothesis is true that our intervention improves outcomes by 6 points, we actually don't have a really good chance of detecting that. We've kind of set ourselves up for failure here because even if this is true, we're only going to get a statistically significant result 54% of the time. And that means we're going to make a type 2 error, right? We're going to miss a result that's really there about 46% of the time. So this is not a really good situation to be in if we actually want to be able to find the result that we believe is really there. So there are a number of things that we can do to improve the statistical power in this situation. And again, statistical power is just the probability of observing a significant result when the alternative hypothesis is true. Right. So we'd like to move this distribution and get more blue on the other side of those statistical significance cutoffs. So there's a few ways that we can do that, right? One, which always isn't always available to us, is increasing the size of the effect, right? If rather than changing it by 6 points, what if I could change it by 10 points and just slide that whole distribution over to 10? Well, in some cases, like in a drug trial, maybe I could do that because I could increase the dose of the drug that I'm giving. But a lot of the time in rehabilitation studies, we may not be able to change the size of the effect, right? The effect of an intervention is probably some fixed value, not totally under our control. But if you're studying like dosing, perhaps, you could meaningfully do this by giving things in a higher dose. Another way we can do it is to reduce variability in the data. So rather than, sliding that distribution over to be centered on 10, if we just make this distribution narrower, now more and more of the distribution is going to be past that statistical significance threshold, and we'll have greater statistical power. So sometimes we can do that, for instance, by having narrower like inclusion or exclusion criteria that should reduce the standard deviation in our data. Sometimes we can do it with strategic use of covariates, right? Controlling for certain baseline variables will reduce that background variation. And I'll go through a specific example where we do that in our R code. Or other times, if we just take repeated observations, right? Sometimes if we have kind of a noisy measure, we should take a lot of different observations and then average those together to get one more reliable observation. And that can also improve our signal to noise ratio. But of course, the most common way that we think about doing this is by increasing the sample size, right? If I recruit more people, then the standard error or the width of these sampling distributions is going to get narrower. And so this is often kind of the first thing that people think about when they think about statistical power is how many people do I need to recruit in order to reliably detect an effect? So that's going to be the focus, of kind of sample size planning today. But I think it's also important to keep in mind some of these other, design-based ways that you can improve statistical power, either by increasing the size of the effect itself, or by using other sort of clever ways to reduce your standard deviation without having to increase your sample size. So, uh, I want to give kind of a high level conceptual overview, right, of what affects statistical power as we've now defined it, before we jump into some of the nitty gritty of, how do I actually run a simulation and how do I do the code to solve for statistical power? And the underlying principles, I would say, are pretty straightforward, but the actual doing of it can get pretty complicated. So let's focus on the principles. And the same three things really trade off against each other when we're thinking about statistical power for any different type of test statistic, whether you're thinking about a z-score, a correlation coefficient, t-scores, f-tests, or chi-squared. Always the bigger the effect and the bigger the sample, the more certain we're going to be in our result, right? Big, obvious things are relatively easy to detect. Small, subtle things are going to be harder to detect. And therefore, we're going to need a larger sample to detect something that's more subtle, right? And kind of keep tipping the balance in favor of our certainty. And those will always be counterbalanced by how much variation there is in our data, right? So something that is pretty small and subtle, if there's not much variability, I can still probably detect that reasonably well. But if my relatively subtle difference now is up against huge variability, by kind of comparison, now it's even smaller. My signal to noise ratio has gotten worse, and that increase in the variance is going to make me less certain. And then the fulcrum, right, kind of the tipping point around which these things rotate is determined by the actual mathematics of, how do we calculate these statistics, and also our alpha and beta rates, right? Which if we go back to the previous slides, alpha is that type 1 error rate. Let's just bring this back, right, to be clear. Alpha is that type 1 error rate, which by convention we use 0.05 because Fisher, almost 100 years ago, suggested that he found zero point zero 0.05 was useful. And basically, that became the standard. But there's reasons why you might want to be more conservative, but there's also good reasons why you might want to be less conservative. So don't feel too beholden to zero point zero 0.05 just because it's kind of the common threshold. There are good reasons to use a higher or a lower alpha value when you're designing a study and considering different tests. Similarly, then that type 2 error rate or the beta is a miss, right? It's this orange part of the distribution over here. There really was a real effect, but we didn't get a statistically significant result, and therefore we would conclude, well, our results are not, sufficiently different from zero that we feel like there's an effect going on here. So ideally, we would like this to be pretty small so that our power can be higher, right? Because power is just 1 minus beta, because it's just this distribution shifting from side to side. So, there are times when we really want these to be like a smaller alpha, and we might want beta to be really high, especially in like later phase research. If I want to set up a really severe test of does my drug work or does my intervention work, might want alpha to be quite low, and I might want beta to also be quite high because I don't want a false positive, but I also don't want to miss any chance that my drug does work. In earlier phase research, though, right, maybe there are different trade-offs there. Like maybe it actually becomes more costly to miss an effect than it is to have a false positive. Because if we've got a couple false positives, maybe those will kind of come out in the wash of subsequent experiments if experiments aren't too expensive and costly to run, right? So it's important to think carefully about exactly how conservative or how liberal you want to be. And there are some references that we can direct people to for that. But I would say the main thing is don't just assume that alpha has to be 0.05. And think about beta kind of proportional to different phases of research and what you might have the resources to detect. So with that in mind, one of the papers we sent out in advance of this webinar that I would strongly encourage everyone to read if you haven't already is this sample size justification paper by Daniel Lawkins. And it goes through how you can do a sample size justification across a number of different settings, right? Where I think we typically think of, oh, I have to determine the number of people I need based on some kind of effect and really do an a priori power analysis. A priori power analysis is great, but it's most appropriate at kind of the end state of research. So Lawkins lays out a number of different justifications. For instance, are you measuring basically the entire population if you've got a really specific group of people that you're looking at, right? And maybe it's a very tiny population that you have access to. Either this could be something because like it's a rare disease population, maybe, or like to use an example, if we're just looking at what do the faculty at WashU think in a survey, right? I might not need standard errors and p-values if like all of the faculty in my department, but one or two responded to the survey, right? Maybe basically I'm measuring everyone in my department and we're not trying to generalize to other departments. Alternatively, there can be things like resource constraints. Are you really looking at accuracy and kind of the width of a confidence interval rather than statistical significance? There's the classic a priori power analysis, which we'll talk more about in a second. There are sort of heuristics and common standards where maybe you just say, okay, in my field, everyone uses a sample of this size. Or there's just not really a great justification. And Lawkins talks through all of these, as potentially appropriate. We're going to focus on two today, though. We're going to start with the a priori power analysis, which is kind of the most traditional approach to sample size justification. And we want to have a good handle on that and what it means. But we're also going to talk about resource constraints and what we might do instead in that situation. Because if I can only afford to recruit 20 people, it doesn't matter what my a priori power analysis tells me. I'm only going to have 20 people, right? And then we're in a very different situation where rather than saying, okay, how many people do I need? I have to say, well, this is how many people I have. Now, what could I reasonably test? And that's something called a sensitivity analysis. So we'll be contrasting these two approaches today, but I would encourage you to look at this paper in more detail, especially thinking about, how you might want to use it when you're writing a grant application and doing a sample size justification there, or with your trainees when they're planning, dissertation studies or something like that. I think this is a very accessible, very well-written paper to get people thinking more critically about their sample sizes. Okay, so first, let's start with an a priori power calculation. And what does that mean? So an a priori power calculation is essentially calling our shot in advance. We're going to assume that there's some true effect, of our intervention or of a correlation that we're trying to measure. There's some known or reasonably estimated variance that we're going to have. And then we're going to plug in specific alpha and beta rates that we might want to use in terms of weighing up the cost of type 1 and type 2 errors. So what we are doing is solving for the sample size that we need, assuming all of this other stuff is true. And this is typically done, before the data are collected, because this goes then into the design of the study. So in an example, we'll talk about in a minute, if I'm looking at something like gate speed, A minimal clinically important difference for gate speed is 0.13 meters per second. It depends a lot on like the population that you're looking at. And again, one estimate of how much people vary in their gate speed as older adults from normative data is about zero point 0.2 meters per second. So we could plug that in. And then if I assume kind of I would call these the default alpha and beta rates of alpha is 0.05 and beta is zero point 0.2, which translates into having 80% power, right? Because again, power is just one minus the beta rate. Then I would solve for, all right, if all of that is true, how many people do I need to reliably detect that effect with 80% power? And then we will contrast this with sensitivity analysis. So this is what we can reasonably detect, assuming that our sample size is fixed. So now what we'll say is, well, I don't actually know like what effects I could reasonably get, but I do know I only have 20 people, right? So I think this comes up a lot, especially in earlier phase work where you're maybe doing like feasibility and preliminary efficacy type analyses. Um, and you'll have a small n there. But another area where you might be doing this type of work and actually have a large n is in work with the electronic health record. Because there, again, you don't have control over how many people meet your inclusion exclusion criteria. You're just going to filter down until you get the sample you ultimately need, and then you'll have that n. So, this could actually be quite a large number if you're working with like electronic health record data. Um, but, either way, whether n is big or n is small, if you have a feasibility constraint and you could say, this is how many people I have, you can do a sensitivity analysis to then say, okay, given how many people I have, and again, given some reasonable estimate of the variance, what kinds of effects could I detect? And when we do a sensitivity analysis, typically what we'll do is we'll then sweep through different sizes of effects and different levels of statistical power, right? Because we might be able to detect some things with 70% power, some things with 75% power, and some things with 80% power. So in a sensitivity analysis, what we'll typically get is several different power curves, as I'll show in a moment. And we can then use those to inform our decision about do we think that this sample size is adequate or inadequate for like a clinically interesting effect, or what kind of effect we might be able to reasonably study. All right, and finally, before we transition into kind of the R focused portion of this, I think one of the key things about sample size justification is to always put your question first and think about, what is the inferential goal of the study? Because those inferential goals are highly specific. So this might seem a little bit pedantic, but this is like when people say it's a well-powered study. You can't really have a well-powered study because power doesn't apply to the whole study. It usually applies to like one specific test inside of that study. So you can have power for a specific test, but that generally does not mean you have statistical power across the study. For instance, if you actually have like a specific a priori outcome at a primary time point and you have 80% power for like a group difference at that time point, that doesn't mean you have 80% power for all other tests, all other outcomes, or all other time points you might look at. Studies often contain a mix of these kinds of confirmatory aims, where there's some kind of called shot that we designed the study around, and then more exploratory aims, where we aren't explicitly powered to detect it, but we're still interested in it and it's worth asking about, right? But the key thing is we might only actually have power for this one, and we don't have statistical power for these other ones. And that's okay. That's a very common limitation. It's very reasonable. We just need to make sure that we're kind of adjusting our confidence and our expectations appropriately. So we often want, power to detect a specific hypothesis in a confirmatory way. We have enough data up front to make a good estimate of what kind of effect we're looking for, what a clinically meaningful effect might be, and then we've collected enough people to rigorously test that effect. But there are also many questions of interest that the study was not designed to test, and therefore we shouldn't have the same corresponding level of confidence in those more exploratory questions. Sometimes also the goal of a study might just be exploration in itself. not every study is like a phase 2 or a phase 3 clinical trial, right? And we're just entering into this investigation, in which case we're not as worried about statistical power up front, or at least having the sample size necessary to like meaningfully test a hypothesis. Because we might just be trying to explore, some of these questions that we need to answer in order to then actually set up a strong test in a future study. Like what is a reasonable effect size? How much variance might we expect? These are what is the dose at which we think we need to reasonably deliver this intervention? Those are all like kind of foreground questions that we may need to answer through exploratory research before we can really set things up for a strong test with an a priori power calculation in a confirmatory study. Okay, so I think that is a good place to transition to the more R coding piece of this, where we'll get into a little bit more of the nitty-gritty of actually doing a power calculation. Um, as I bring that up, if anyone has any like conceptual questions, I feel free to like pop those into the chat. We can stay on that for a minute. Um, or if folks feel more ready to jump into like, okay, show me some R code and how do I actually do this? Um, we'll move forward there. Um, Again, I'll put this link into the chat. So I'm showing you in my window now my GitHub repository. You don't need to do this to follow along, but if you are really interested, you can click on that link. And we have a copy of the slides here that I'm showing you. That's the DAPR sample size V2 PDF. And then there's two documents also in here, sample size justification underscore gate underscore v6. That this is the R Markdown document that contains code. So if you're proficient with R, you can download this file and you could actually like open it up and run it now, or you could adapt that code for the future. Um, if you're not proficient in R, feel free to click on this one that says v6 HTML, or you can just follow along. But I'm just going to show you basically if you click on that in GitHub, unfortunately, it opens it up like as raw code and doesn't actually render it as an HTML file. So what you'll have to do is click on download the raw file, and then you can open up this HTML document. So again, you can just follow along with this for the purposes of the webinar. But if later you do want to look at this in more detail, feel free to either use that R Markdown file or just, open the HTML file to kind of follow along. All right, so let's go ahead and look at this in a little more detail, where again, we're going to do two examples. One is an a priori power analysis, and the other is a sensitivity power analysis. In either case, one of the first questions that we're going to need to answer is, what is the smallest effect size of interest? Or, what kind of effect are we reasonably interested in? Some of you might be familiar with like Cohen's d as a standardized effect size, or R squared as a standardized effect size. And sometimes people will use like a rule of thumb, like, well, we want to be able to detect a Cohen's d of at least 0.4, because that's a quote unquote, moderate effect size. But if your outcomes actually have units and people have been studying those outcomes for a while, we can probably do a little bit better than that and select some kind of like minimum clinically important difference. So for instance, let me pull up this super handy pocket guide that was kindly put together by our friends at the ANPT. This is a great summary with lots of normative information about the 10-meter walk test. So let's say that I'm doing an intervention where my primary outcome is the 10-meter walk test. This gives me lots of useful information about important changes in gait speed. So here they've nicely summarized data from a number of different studies, whether it's in Parkinson's or spinal cord injury or stroke. And this ranges, I think the smallest is like a 0.11 change. Yep, there's that, up to about a 0.34 meters per second change. So in a practical sense, you would actually choose one of these that corresponds to the population you're interested in, right? Whether and even within stroke, you have to consider, okay, is it acute stroke or is it chronic stroke? But for me, I'm just going to say, okay, basically these range from about 0.13 to zero point 0.3 meters per second. So I'm going to pick the more modest 0.13 meters per second. And part of the reason I'm doing that is because even if you find a paper in your population that reports a minimum clinically important difference, despite what the minimum in that name implies, that's still an estimate of kind of what the most important difference is. So there's going to be some sampling variability to that. So there's probably a 95% confidence interval around that MCID, and you might want to pick kind of the lower limit rather than picking just what's reported as the MCID. So again, this can be a hard question to solve if there's a range of studies. But in general, I would say among the possible effect sizes you think are important, it's generally going to pay to be conservative and pick something closer to a smallest effect size of interest, because then that's going to actually give you a more conservative test, and a bigger sample size. And unless you're doing an intervention where there's actually, a very real cost of risk to your participants, usually we err on the side of over recruiting or getting more people is good, right? If there is a real demonstrable risk to participants, then that calculus gets a little trickier and you don't want to over recruit. But by and large, science suffers from not having big enough studies. So err on the side of caution and try to recruit more people. The other thing that we'll have to try to estimate is some kind of standard deviation. Remember, I said we always need some estimate of the variance in addition to the effect size. So again, you would hopefully be able to find some estimate of this, and again, take a conservative estimate in your specific population of interest. But I was able to find, for our purposes, this paper, which had some really nice normative data across different age ranges of adults, where if we just look at community dwelling older adults, their typical standard deviation is about 0.2 meters per second. So if 0.13 is my effect size and zero point 0.2 meters per second is my standard deviation, then the effective Cohen's d here is about 1.3 divided by zero point 0.2, about 0.65, which is sort of a moderate to large standardized difference. If I'm trying to say like, okay, I want to be able to detect at least a difference of 0.65 between my two groups. So if I'm doing this then as an a priori power calculation, again, in my hypothetical gait intervention, I want to say, does a novel gait rehabilitation intervention improve gait speed by at least 0.13 meters per second compared to standard care after controlling for baseline gait speed? Because we're actually going to set this up as an analysis of covariance or an ANCOVA where I control for baseline. And we'll talk a little bit more about why that's important to do. But basically, if I've got my two groups, I know what my smallest effect size of interest is. I'm going to pick, a specific post-intervention outcome, and I then want to know how many people do I need in order to reliably detect at least the smallest effect I'm interested in with 80% power. So this is where controlling for baseline actually becomes really important, because if I don't have baseline, I probably don't have as strong of a test as I potentially could. So it's always good to collect baseline data. And furthermore, rather than using kind of a repeated measures ANOVA approach where I treat like pre-intervention and post-intervention as categorical factors, it's actually statistically better to just look at the post-intervention and then control for baseline as a covariate. And if you're interested in some of the reasons for that, there's this really nice paper. It's very short and accessibly written by Vickers and Altman. It's down in the reference section of this handout. But they nicely kind of contrast why would you control for baseline rather than doing a repeated measures ANOVA. Now, building on some of the previous presentations in this series, like we had Aaron Caldwell on last month to talk about the superpower package, there are really handy tools, both in R and in other software, to do this kind of power analysis for you. And the superpower package does support ANCOVA. It has some pre-built functions that we'll use in a second. But for this example, I'm actually going to implement like a custom simulation so we can see exactly what's happening under the hood rather than letting superpower do these simulations for us. So what we're going to do is a pretty easy process. Um, but in terms of coding and implementation, it can get a little bit more complicated. But if you're trying to do a simulation-based power calculation, the kind of the algorithm or the steps are the same, and they're pretty straightforward. Basically, we're gonna assume that like the what we want to see is true. We're going to assume that the variance is zero point 0.2. We're going to assume that there's a minimum clinically important difference of 0.13, and we're going to make fake populations from which we can sample. So we're going to repeatedly draw baseline and post-intervention gait speed values for each group. So we're going to simulate a control group. We're going to simulate an intervention group. In every run of that simulation, I'm going to fit my model to the data set. So in this case, it's just post-test as a function of what group you're in, controlling for baseline. You probably have other models and other questions that you're interested in. But again, the logic is the same. You know, you get to make believe that your alternative hypothesis is true and you simulate it, fit the exact statistical test that you want to do in each run of the simulation, pull out the p-value for the effect or the effects of interest, and then you can estimate power for the proportion of statistically significant results. So I don't want to belabor the R code too much here in the recording session. I think when we open it up to Q&A, I'm happy to like jump around and go back through all these different things. But that is essentially what I'm controlling here. I'm going to set the mean for my control group at baseline, the mean for my intervention group at baseline. I'll program in the MCID. I'll program in the standard deviation. And I'm going to control these simulation parameters up here in this chunk of code. And then I have some outputs that just kind of confirm that, yes, the computer is like calculating things correctly the way that I would want. Oh, the other parameter I will mention here, because I don't think we've actually talked about that yet, is I need to control the correlation between my baseline and my post-intervention assessment. Because the less correlated they are, the less it helps me to actually control for baseline. And in this case, I chose zero point 0.7 because gait speed does tend to be pretty strongly correlated from baseline to post-intervention assessments. So usually like, 0.5 is probably a reasonable starting point, assuming that these things are at least somewhat correlated over time, but potentially this can be quite a strong correlation. And if you actually have empirical data on what that correlation is in your population, you can plug that in here. If you don't have that kind of information, you can take a guess, like I've done here, and then you can also then in your simulations go back and change this parameter to see how it affects your estimate. So again, I'm going to gloss over the R code a little bit for now, but then I'm very happy to open that up to other people's questions when we get to the non-recorded Q&A. But in essence, what I'm going to go through is apply the same statistical test, right? I'm going to draw a random sample from the population, do my statistical test, go back, draw another random sample from the population, and do my statistical test. And I'm going to do that for a bunch of different sample sizes. Specifically, I'm going to do it from samples of size 10 per group to 50 per group in increments of 2. So the first time around, I'm going to simulate 1,000 experiments with 10 people per group. And once those 1,000 are done, I can estimate the power. I'll then move to 12 people per group, simulate 1,000 more experiments, right? Pull out my p-values, see how many are statistically significant, and then move on to 14. And that is basically what is happening here. I've got this to output the current n per group that we're testing, and then the resulting statistical power, which is just of the 1,000 simulations we did, what proportion of them had a p less than 0.05? And you can see that with 10, our power is only 46, which isn't great. But as this goes up, right, eventually we cross that threshold of 80% power, which we were looking for at an n of about 22. And as we add more and more people, we get kind of diminishing returns. So again, if you were doing this yourself, right, you could change these different parameters, or you could look for a different level of statistical power. But the general logic remains the same. we're going to set up, the alternative hypothesis, the make-believe thing that we would like to see happen if our hypothesis is true. Then we'll simulate data at a bunch of different sample sizes. And then we will just store the results. And here again, this is the exact same as kind of that printout that we had before, but now what I'm showing you is the estimated power at each sample size. And if our criterion was, 80% statistical power, we first cross that when we get to 22 people per group. If you were really, worried, like maybe this is a very expensive intervention, you might want to know, okay, do I really need 22 or can I get by with 21? And in which case you might go back and where we set that like n search parameter, you could, okay, rather than steps of two, let's do steps of one. But rather than stepping from 10 all the way up to 50, maybe I'll just go from, like 18 to 26 or something like that. So you can also do this in like an iterative way because it does take a bit of time to run. So usually what I would do is set up these simulations to run across like a very wide range in terms of total number, but also go in like pretty big steps. So I might start with like steps of 10 more people. Once I find the range where it seems to be important, then I'll zoom in to redo the simulation and say, okay, let's look at the range where I know I'm going to cross my power threshold. And now I'll add like one person at a time. And then to see, because sometimes it makes a difference. Oh, yes, I see a question in the chat if the webinar is going to be uploaded. It will be posted on the DAPR YouTube channel. And we usually email that out when posted and also promote it like on social media. So if you're on the DAPR mailing list or follow DAPR on, LinkedIn or Blue Sky, hopefully you'll see it. It usually gets posted about a week after we're done, but we will definitely be posting the recording and again, access to all of the handouts and slides. All right. So again, with this is great. We've done basically an a priori power calculation to say, okay, if my minimum clinically important difference is 0.13 and everything else, I need about 22 people per group. But that's also assuming that the true correlation between baseline and the outcome is zero point 0.7. So one of the things that we can also do then is the exact same process. Now we'll do these simulations, but we'll change the size and the strength of that correlation. This gets tricky though, because basically the more parameters you want to simulate over, right, the more and more time your computer is going to be sitting there grinding through all of the different iterations. But we can do that. And you can see then, okay, I've programmed this then to say, all right, so what's the minimum n when we cross that 80% threshold as a function of what the correlation is? So this is the output in tabular form. This is the output in a graphical form. But you can basically see, all right, if there's no correlation, I actually need 40 people per group, 80 people total in order to achieve 80% power. And that's crazy, right? Think about that compared to when we actually have the correlation. With a correlation of zero point 0.7, I only need 22 people per group or 44 total. So I need more than double the number of people if I didn't have that baseline variable in there as a covariate. So when I actually have really strongly correlated covariates and I can put them into my model, that can be a huge power saver for me if that covariate is strongly correlated with the outcome and relatively independent of the variable of interest. So in an experimental design like this, that's great because baseline gate speed should be independent of what group you got randomly assigned to. In observational data, it doesn't always work out that nicely because you can't control what variable is correlated with what, and you may not get that power saving effect. But you can also see that if it was, even more strongly correlated, maybe I only need 14 people per group. But if it's a little less correlated, I need 26 people per group. So we can kind of titrate then our sample size planning based on how confident we are in that estimate of the correlation. Because again, if zero point 0.7 is a really reasonable conservative estimate, 22 people is great. If I'm a little less confident in that and I can afford it, maybe I want to put 26 people per group into my grant application, right? We can adjust our estimates based on these different considerations. So then when it actually comes time to write that up into a paper, here's an example sample size justification consistent with what Lakens asks us to include in his 2022 paper. In this case, the primary analysis is an ANCOVA testing the group effect on post-intervention gait speed after controlling for baseline gait speed. We set alpha equals 0.05 and targeted 80% power. I added this little bit about kind of conventions about power. And then we have some other information about like the MCID and that kind of stuff. So the let me toggle back to my slides though, just for a second because you can look at my specific wording again in that example if that hopefully helps you kind of write up an analysis for a paper. But this is the table from Locken's paper where he specifically says, okay, well, what are the things you need to take into account? And he has these 6 things that you should report when you are reporting your sample size justification for an a priori power analysis. So I tried to make sure that all 6 of those are in there for the example that I have provided for you. But again, if you have a very different design or something, right, the exact wording and what you have in there is going to be a little bit different. So just make sure that when you're reporting your a priori power calculation, all of these things are taken into account and transparently reported in your sample size justification. All right, so let me toggle back to the HTML document. And again, quickly, I want to step through kind of a sensitivity power analysis and the general logic of how that works. So we can open it up to have like lots of time for Q&A and kind of the interrogation of the R code. But any general questions about a priori power analysis from folks before we move on? All right, not seeing anything in the chat. I'll keep moving forward. Okay, so for this next example, I'm going to change the design. We'll keep our outcome the same, but just to kind of highlight that like you can do this for all kinds of different designs. And again, basically, if you know the analysis, you can simulate it. And either with the help of your friendly neighborhood statistician or with the help of, generative AI, you can probably then say, here's my design, here's my analysis, help me write the simulations to do some of this stuff. But for ours, what we're going to do is a sensitivity power analysis, and we're going to use the superpower package in R because it actually has some built-in data generation functions that once you get used to kind of its syntax, will save you a lot of time. And this is specifically for factorial design, so kind of our traditional, ANOVA or ANCOVA designs. So in this example, let's assume that gait speed is still the thing that we're measuring, but we've got our intervention group and our control group. And now I'm actually going to analyze 3 time points. I've got baseline, I've got post-test, and I've got some kind of long-term follow-up. So our this would be a 2 by 3 factorial ANOVA. And the thing that we're really interested in here is the group by time interaction. However, in this example, let's say that, I had a pilot grant from my university, and I could only get a total N of 20, 10 people per group, right? So my resources are fixed. I wasn't able to, really do an a priori power analysis to recruit as many people as I would like. I'm stuck with the 20 that I have. And now what I would like to know is what could I reasonably detect? Because that helps give me a little more confidence in how I interpret both statistically significant results and non-significant results, right? Or how much I should read into some of my confidence intervals when I look at the data. And typically, right, this is going to be more appropriate for earlier phase research when we aren't really setting up a strong test of the null hypothesis, because we're often going to be underpowered. So what we'd like to know is, well, just how underpowered are we? so that I can interpret my results with a little more confidence. The other thing I'll add here is that with 3 time points, we actually have 2 correlations to consider rather than just one. I need to consider the correlation between like adjacent time points. So this would be like pre-test to post-test, and then this would be post-test to the follow-up assessment. And then I also need to consider the correlation between non-adjacent time points. So this will be a second correlation for those more long-range autoregressive effects. So let me scroll down. Here's just this is if you are using superpower in particular, this is helpful for thinking about the correlation structure. I've got 2 groups and then I have my 3 time points. So what I'm going to do is build a correlation matrix. So it's a 6 by 6 matrix, right? It's my group at 1 at baseline, group 1 at post-test, group 1 at follow-up, group 2 at baseline, group 2 at post-test, group 2 at follow-up. And then I'm going to fill in all of the different correlation values. So again, within each group, I'll have correlations for neighboring time points. For the between groups, they'll just be 0 because the people in the intervention group should, in theory, have nothing to do with the people in the control group. And then within my second group, again, I'll have those correlations for the neighboring time points. So you have to set up this correlation matrix in order to provide the lower triangle of that correlation matrix to the superpower package. So again, this is something, if you're working with superpower, you can look at their help documentation, or again, actually, because these things are available online and language models can interact with the help documentation, it's actually pretty good at helping you troubleshoot some of these issues if you have questions about how to set it up. Just always make sure you're validating whatever, the chatbot tells you, because otherwise it might not be correct. But ultimately, this is the correlation matrix, I should say the lower diagonal of this correlation matrix is what we're going to be feeding into the superpower package. In addition to the specifics about our cell means. So for this example, again, right, we've got kind of a fixed sample size constraint. We've got 10 people per group. We're going to keep that 0.2 meters per second as our overall estimate of the variance. And then I can program in, what might I reasonably expect in terms of the change in gate speed over time. And so in this example, right, what I'm going to do is I'm going to make sure that my control group kind of improves modestly, as we might expect. And then my intervention group is going to be 1 MCID bigger at post-test and remain 1 MCID bigger at the follow-up assessment. So the difference between my groups is 0 at baseline, and then it's just the MCID at each subsequent time point. One really nice feature of the superpower package is it outputs this graph for you, which this is if the alternative hypothesis is true, right? This is our simulated reality where we're pretending that this is really the case. This is our intervention group at baseline, and this is how they progress through the study. This is our control group at baseline, and this is how they would progress through the study. I can then, using superpowers built-in, simulation tools, pass the ANOVA power function, my design, my alpha level, the number of simulations I want, and then it will simulate that 1,000 times and give me my answer, which for this particular circumstance is not great, right? With only 10 people per group, we only have 35% statistical power for that group by time interaction. But that's okay, right? Because again, what we actually want to do here is not an a priori power analysis and just say, well, okay, we're going to do one situation and see what that looks like. We're going to do a sensitivity power analysis. So yes, our power doesn't look very good right now, but let's loop through a few different examples. And in the code below, I've tried to provide you with code to do that in like a more automatic way. But if that feels a little intimidating or you want to start out with something a little simpler, you don't actually have to do any of the fancy looping stuff that we're going to do down below. You could just go back and change your parameters up here and say, okay, well, what if my mean differences were bigger? What would that power look like? Or what if my mean differences were smaller? What would that power look like? So once you're able to do this once, you can actually do this by hand multiple times to do your sensitivity analysis, right? There's nothing wrong with that. It's totally fine to go back in and just plug in different numbers and say, okay, well, when can I reasonably detect something that is clinically interesting? In the code that I have down below, though, we're just going to do that in a more automated way where, remember I said basically groups are no different at baseline, and then they are one MCID different at the post-test and at the follow-up. Well, what I'm going to do is I am going to adjust the size of that MCID difference. So I'll say, what if it's, half as big as what I put in originally, or three-quarters as big as what I put in originally? At one, that will be just as big as what I put in originally, right? And then eventually it will go up to like, all right, well, what if this difference is twice as big as what I originally put in? And then what we'll do is we'll keep changing those mean differences. We'll keep running it through the superpower package, and then we will keep calculating statistical power. And if we do that, this is, what we get kind of as an output from in a text-based format. If we want to look at that though as an actual sensitivity curve, again, I have the R code for setting that up, but you can see, all right, if our groups are one MCID different at post-test, right, the corresponding power there was just over 35%. So that's this green dot here. We don't actually hit 80% statistical power until it's at least 1.75 times greater than the MCID, right? So with 10 people per group, if we had a non-significant result, we probably can't really conclude much because we could reasonably miss a lot of effects that are pretty important, right? Like if the real effect was 0.13 meters per second, we probably are going to miss it with 10 people per group. But if it's a really big effect, it's unlikely that we're going to miss that with only 10 people per group. So this would be a good example of, all right, well, we have sensitivity to detect really big, massive things, but we don't really have the sensitivity to detect our smallest effect size of interest with only 10 people per group. And again, if we wanted to report that, I have a text example of exactly how I might write this up to put into a paper for this kind of preliminary study. But if we go back to the slides for a second, again, we can look at, what Lakens recommends when reporting a sample size justification based on resource constraints. So again, do you have a specific text example in the handout for like kind of how I would write up that gate analysis? But if for your specific situation, you can refer to Lakin's paper for these different considerations for okay, assuming that I'm just constrained by my resources, how should I write that up as a proper sample size justification? All right. So I'm a little bit behind where I wanted to be in order to leave us like a full 30 minutes for Q&A, but we're pretty close. Let me go through just a few broad conclusions, and then we'll open things up for Q&A. My first thought is, I think all studies need some kind of sample size justification or consideration. So that should always be like in any grant application you're submitting, and it should be in pretty much any paper that you're writing. But that doesn't mean that every study needs to be a phase 3 clinical trial, right, with an a priori power calculation, whoops, and 90% statistical power. Lots of studies are going to be small, preliminary, and exploratory, and that's fine. The thing is, we just need to correctly label them as such so that we can adjust our confidence in the results appropriately. And therefore, the study needs a sample size that is justifiable given its inferential goals, right? So if your goal is more on that exploratory side, you can probably get away with a smaller sample and a weaker justification. If you're trying to make a really big, bold claim, you probably need a larger sample and a tighter justification in order for people to have a lot of confidence in that result. Similar or along those lines, though, power analysis or other sample size justifications are not easy, nor are they fast. This is actually probably one of the most time-intensive things I do as an applied statistician, working with a lot of different faculty in my department. So if you have ever felt like power analysis is confusing and hard to do, That's just because power analysis is confusing and hard to do. So I think the best things you can do are take your time, gather all of the relevant data that you can find to help inform some of those that assumptions that are going into it. If available, I would highly recommend, you work with a statistician, especially if you have a very unique kind of analysis that you're trying to design the study around. But this is where I'll also say, as generative AI keeps getting better, if you've got a relatively standard design, you've got a known software package like Superpower, you can get pretty far by asking, going back and forth with your chatbot to help you walk through creating simulations, and then changing the parameters of those simulations and doing it again to get different estimates of statistical power for a number of different alternative hypotheses or a number of different research contexts. Also, power analysis is highly specific, right? If you remember, we were talking about like you can't say the whole study is well powered. It applies to a very specific statistical test and outcome and time point. The other thing then is if you plan to run a certain kind of model, build your power analysis around that model. I'll see this a lot when I'm reviewing papers where people will say, okay, well, we powered the study for this between group comparison, and it's a t-test. But then all of their analyses are based on a group by time interaction in an ANOVA. And then there's a disconnect between what you actually powered the study for and how you actually analyze the data. So in general, try to be as specific and consistent as you can. If you do need to simplify something for some reason, like maybe you have a very complex design and you just need to make it more feasible for some of the assumptions that are going into your power analysis, that's okay. Just try to be really transparent about what is simplified and how it aligns with your study aims. And finally, always put the research question first, right? I think this is one of the other challenges sometimes in talking to faculty is that we want, like the sample size calculation. How many people do we need? How many observations do I need? But we haven't actually answered the more important issue, which is what is the question, right? We don't want to put the cart before the horse here. And it's better to have, a very clearly articulated hypothesis with a more approximate approach to the sample size than to have a wonderfully specific sample size estimate that only vaguely relates to your hypothesis, right? So always put the research question first, because that's going to guide everything else in the design of the study. So with that, I'll just plug Repro Rehab and the DAPR Center one more time. Thanks everyone for coming. I'm going to go ahead and stop the recording.